Okay, so this is problem 2-124. Okay, and it's a 3D problem. And what we're given as this force vector at the end of the end of this apparatus, and we're given that it is 400 I minus 200 J plus 500 K. Okay, so that is the force vector. All right, and what we're looking to find is the component of this force vector that's directed along cable CA here. So directed along cable CA. So any component that's perpendicular to this cable CA will not influence the component directed along CA. So what we're trying to find is the magnitude of the force directed along CA. So the magnitude of the force directed along CA. All right, so let's start the analysis. The first step of this analysis is to figure out what direction CA actually is. So we'll make a position vector from C to A, so position vector from C to A. And if we look at the diagram here, we see moving from C to A in the X direction, that is 6 meters. So we have 6I. Moving from C to A in the Y direction, right, we're moving closer to the origin here by 1 meter, so that's negative 1J. And lastly, in the Z direction, from C to A, we're actually moving downwards 3 meters, so that's negative 3K. All right. And to be able to tell the direction of this vector, we also need the magnitude of this vector here. So to find the total length of the cable, or the magnitude of the position vector RCA, we just take the sum of the squares of these components and take the square root. So we have 6 squared plus negative 1 squared plus negative 3 squared. And then don't forget to take the square root of all that. And what this comes out to be is we have the magnitude here, which is equal to 6.782 meters. So that's the total length from C to A. Now, the total length doesn't really help us a whole lot. What we really need is the direction of this. So we'll transform our position vector RCA into a unit vector UCA. So this unit vector UCA. And what UCA is a vector that has a length of 1 directed right along the same direction as the cable CA. I didn't draw that perfect, but you get the idea. So a unit vector, so length of 1 directed along CA. And the way we do that is we take the position vector and we divide it by its magnitude, or its length. So we take the full vector and we divide it by its length, and that should scale everything so the unit vector is size 1. All right. So we just take 6I minus 1J minus 3K and just divide all that by 6.782 meters. So we'll take each of those components and divide it by this magnitude. And what that results in is we get a unit vector of 0.8847I minus 0.1474J minus 0.4423K, right? And let's just write down the force vector again so we don't have to keep scrolling back up. So that's 400I minus 200J plus 500K. All right. So to simplify this, to give you more understanding, so if we had a vector just f, and we were looking for the component of this vector along, let's say, the unit vector AB. All right, we would do nothing other than just take the scalar product or dot product f dot u AB. So that's all we need to do in our example, which is 3D. So in the 2D example, we would get this, and we'd get some component f AB. All right, so let's do this for our problem here in the 3D terms. So to take the dot product of these two values, I'm just going to erase this quick. Okay, so to take the dot product, we just multiply the corresponding components together and then add all the values. Okay, so we multiply these two together and we add them to the multiplication of these two values, and we add them to the multiplication of these two values. So we have FCA, the force directed along the cable CA, is equal to F dot UCA. Okay. So we have 400 times 0.8847 plus negative 200 times negative 0.1474 plus 500 times negative 0.4423, right? And that comes out to be, remember that in a scalar product we input two vectors and we just get a single value out of it. So the force directed, and I must be careful here because we're talking about the magnitude, we're not talking about a vector here. So I need to make sure that I'm putting the magnitude there. And this comes out to 162 newtons, right? And that's our answer to problem 2, 124.